Hello, everyone. I'd like to welcome you to this talk, and I'm very grateful to the session conveners for giving me the opportunity to share this research with all of you. So to introduce myself, my name is Justin Mistakawi. I'm currently a PhD student at the University of Wyoming, and my main research focuses on economic and structural geology. But today I'll be talking to all of you about metal release and its impact on regional hydrochemistry and biogeochemical cycling in a historic mining quarry in western Massachusetts. So just for our geographic framework, here we are in the great state of Massachusetts, and the quarry we're interested in is the Osborne Quarry, which was historically mined for soapstone between the mid part of the 19th century up until about 1920. So the Osborne Quarry is in the town of Blandford, which is about 40 kilometers south of Amherst and about 35 kilometers west of Springfield. And so if we look at the regional geology, we can see that the Osborne Quarry, here in red, as well as Springfield's water supply land, here in black, are situated in this well-drained crystalline bedrock basin in which the major rock is politic schist. And so if we zoom in and take a close look at the geomorphology of the deposit, we can see the main mining trench quite well right here. And I want you all to notice just how close it is to this reservoir. I mean, it is literally within 10 to 20 meters of it. And so you can imagine that the chemical weathering of the quarry is going to impart quite an effect on the water quality. So this is that same digital elevation model with some geologic units overlain over it. And let's look at that in closer detail. We have several units here that are of importance. The first is this light blue unit, and that's going to be our main soapstone mining exposure. Immediately on top of it is, in this thin green, is a layer of chlorite schist. And adjacent to that chlorite schist is asbestiform hornblendite, here in the green and orange. And all of this is surrounded by regional politic country rock. And so just to reiterate, this historic quarry is very close to the Cobble Mountain Reservoir. And this is important because the Cobble Mountain Reservoir hosts 23 billion gallons of fresh water for Springfield and its 155,000 inhabitants. And so fundamentally, we really want to understand, how do historic mining exposures influence local metal release and regional hydrogeochemistry and water quality? Fundamentally, we need to consider the interplay between ultramafic mineralogy, chemical alteration, and those effects on local metal cycling and water quality. And so in order to sort of attack this question from the bottom up, we're going to have to address three primary questions. The first, which minerals contain metals in them? The second being, what is the bulk rock concentration of those metals? And lastly, and perhaps most significantly, how mobile are the metals? What sort of environmental impact are they going to have? So let's look at the quarry real quick. Here I am for scale, and this vertical face that I'm looking at is the main soapstone exposure that was mined. On top of that soapstone exposure is a thin layer of chlorite schist. And if we were to continue going uphill, we would run into hornblendite. And so this is an actinolite hornblendite. And I want you all to immediately notice that there is a very strong weathering front on this rock. We can see some rust forming. So that implies that some of the iron that's in this actinolite is being liberated. So we need to think about what other metals can we substitute into actinolite. And if iron is being released, are those metals being released as well? And so in order to explore the mineralogy of these deposits, I made thin sections of collected samples and analyzed them in the optical microscope and also in the SEM. And so here are some cross-polarized light images of soapstone and some plain polarized light images of soapstone. And so just for context, soapstone is altered ultramafic rock that predominantly has talc and serpentine in it. And so talc is right here. It's very platy and plain polarized light. It's gray, it's kind of grungy looking. And serpentine is this acicular or needle-like phase that is very prominent in all of these images. And so this is specifically chrysotile. I want you also to notice that in addition to these two phases, there's also magnetite, which is this opaque mineral here in these plane polarized light images. And so magnetite is iron oxide. So similarly to actinolite, it's conceivable that we can substitute trace metals in for iron in this crystal lattice. And so if this magnetite is being weathered, then perhaps it's releasing dangerous trace metals as well. So let's look at the chlorite schist next. And once again, it's made up mostly of platy chlorite, but it also features magnetite as well. And similarly to our soapstone, this magnetite is very euhedral. It has very well-defined grain boundaries. And so this is an SEM image of that chlorite schist, just to give you an idea of sort of the morphology of these crystals. And so lastly, we looked at this asbestiform hornblendite. I already showed you the actinolite. The other asbestiform amphibole mineral that we care about is amphipholite, which similarly to actinolite can also bear iron and other trace metals, but it's also more asbestiform or acicular. It has more surface area, it's more needly. And so because it has more surface area, it's more susceptible to weathering and metal release. And so here's some SEM images from that actinolite unit, and we can see that there's also magnetite in this rock as well. But unlike the chlorite schist and the soapstone, this magnetite is not euhedral. It's highly amorphous, so it has a lot of grain boundary space, and as a result, a lot of surface area. So it is especially susceptible to weathering. Now, in these bright images over here is an SEM hypermap, just showing us the rough elemental distribution with space in these crystalline phases. And so you can see that this magnetite, in addition to having iron, also features manganese, cobalt, magnesium, and chromium. So we performed a similar analysis for the actinolite, and once again we can see that the actinolite also features some metals in it. But before I talk about this, I just want to point some things out in this image right here. So we have actinolite and chlorite, and right on the very grain boundary of the actinolite is this dark gray rind, which is made out of quartz. And so I've interpreted that this is actually a weathering rind. And this really bright phase here, as indicated by our hypermap, has abundant metals in it. So let's look at that metal concentration. So you can see it has about 10% silver, 6% nickel, some sulfur, and trace amounts of cobalt. And so what I think is going on here is we've had intergranular flow of meteoric waters. And as those meteoric waters interact with this mafic to ultramafic mineralogy, it's scavenging out trace metals. And thus the fluid hits supersaturation. So when that fluid comes into contact with any dilatant or open space between grains, it precipitates out a metal-bearing phase. And so that's the metal-bearing phase we're looking at right here. So now we've looked at the minerals, let's look at the bulk rock concentrations. So the bulk rock metal concentrations for our various metals of interest are in the gray bar, and these were determined by handheld XRF. And these concentrations are in milligram per kilogram or parts per million. So you can see relative to the average crustal concentration of these metals, our rocks in the Osborne quarry are highly enriched. However, a very small component of those, as shown here in blue, is actually bioavailable, which implies that our water quality and our local metal release doesn't immediately pose a threat to biologic uptake or organisms. However, a significant amount of these metals are strong acid available or extractable. So they have the potential to be weathered out in subsequent years. So we've looked at metals in the rocks. What about metals in the water? That's what we really care about, right? And so if we look at stream water concentrations between high flow or spring and low flow in the summer, we can see some pretty stark differences. So during the spring, when there's a lot of water, and when it's just flowing past the rocks and not really reacting with them, there's essentially a negative or a negligible amount of metals being retained in the fluid. So this really isn't of immediate concern. However, during the summer, especially within the mine, we can see that the waters are highly enriched in particularly nickel and manganese. But despite this enrichment, the waters are within safe drinking water standards as prescribed by the EPA and the WHO. And so what are the implications here? Well, the bulk rocks in the historic Osborne quarry are in fact highly enriched in trace metals. And those are associated with talc, other sheet silicates, magnetite, and weathering related phases. Despite this high abundance of metals, less than 0.5% is bioavailable. So those don't immediately pose any harm to our water quality. However, 20% were strong acid extractable. And so in thinking within the context of an intensified hydrologic cycle and increased carbon in the atmosphere due to climate change, we can potentially see that this would be problematic in future years. Because as we increase the volume of rain and the acidity of that rain, some of those strong acid extractable metals in the deposit might be leached out. However, for now, our water has met the EPA standards, implying that hazardous metal leaching is limited by retention in silicate and oxide phases. Thank you so much for attending this talk. I would be very happy to answer any of your questions.